Hello, in this video we're going to go over complex numbers. You're going to see everything you need to know about complex numbers that are used in math competitions. First, what are complex numbers? The first thing we need to know is the way they are represented. The first way of representing a complex number is what we call the standard form of a complex number, which is z equals a plus bi, where a and b are real numbers. A is denoted by real part of z and b is denoted by imaginary part of z. The conjugate of a complex number is a minus bi, and its absolute value is the square root of a squared plus b squared. But what do these quantities mean, and how can we represent them geometrically? Geometrically, every complex number can be placed on a complex plane. The horizontal line is all real numbers, and the vertical line consists of all numbers of the form b times I, where b is a real number. Absolute value of z represents the distance from z to the origin, which is why it is the square root of a squared plus b squared. Now let's look at some of the major operations of complex numbers. We can easily add complex numbers and subtract complex numbers by combining like terms. In order to multiply complex numbers, you simply just use the distributive law and use the fact that I squared is equal to -1. In order to divide complex numbers, what we do is we multiply the numerator and denominator by the conjugate of the denominator, and we notice that the multiplication of a number and its conjugate is absolute value of that squared. Let's now go back and look at the picture that we had and understand the real part and imaginary part of a complex number using the angle theta. If you look at this diagram, there is a right triangle in this diagram, and the right triangle that connects O, Z, and A can be used to evaluate sine and cosine of theta. Cosine of theta is adjacent, which is A, divided by the magnitude of Z, which is the distance from Z to the origin. And sine of theta is the opposite, which is B, divided by absolute value of Z. Taking these and plugging back into the formula for Z, which is A plus BI, we get absolute value of Z, parentheses, cosine of theta plus I sine of theta. Now let's use some facts from calculus. We know the power series for cosine and sine. If we take the power series for cosine and sine, which are 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial minus plus so on, and for sine is theta over 1 factorial minus theta cubed over 3 factorial plus theta to the fifth over 5 factorial, etc. And use the power series for e to the power of x, we get 1 plus I theta over 1 factorial plus I theta squared over 2 factorial plus I theta cubed over 3 factorial, etc. If we take cosine of theta and I sine of theta, it happens to be e to the power of I theta. If you don't see that immediately, I would suggest that you pause the video right now, work on that, and see how that actually does give you the equality. Next, if you look at the formula, cosine of theta plus I sine of theta equals e to the power of I theta, and notice that cosine and sine have period 2 pi. That tells us that e to the power of I theta and e to the power of I alpha are the same if and only if alpha and theta differ by a multiple of 2 pi. One thing that is really useful when you're solving problems involving trigonometric functions is to know the relation between trigonometric functions and complex numbers. And the equalities that are used are these 4 equalities. Sine of theta is e to the power of I theta minus e to the power of negative I theta over 2i. It is also the imaginary part of e to the power of I theta. And cosine of theta is the sum of them divided by 2, and it's also the real part of e to the power of I theta. If you would like to see how these are used in deriving trigonometric identities, I'm going to place a video on the screen that you can check that out. And the last thing we're going to talk about is taking roots of complex numbers. Imagine you have a complex number c and you want to find the nth root of this complex number. All the nth roots satisfy z to the power of n equals c. So what we do is we take c, we write it down as absolute value of c e to the power of I alpha, then we take the nth root of both sides. Nth root of absolute value of c is going to be a positive number, assuming that c is non-zero. Nth root of e to the power of I alpha is going to be e to the power of I alpha divided by n. However, because of the fact that e to the power of I alpha is periodic, we can add multiples of 2 pi to alpha and get the same result. In other words, the nth roots of c are going to be nth roots of absolute value of c times e to the power of 2k pi plus alpha I over n. But because the exponent is going to be periodic, we don't need to evaluate this one for all integers k. Instead, we can just evaluate this for k equals 0 to n minus 1. In the special case where c is 1, we get what we call the nth roots of unity. And the nth roots of unity are going to be e to the power of 2 pi I k over n, where k is an integer from 0 to n minus 1. If you want to see how these are used in solving problems in math competitions, check out the next video on this screen. If you enjoyed this video, make sure to subscribe to the channel, tell me in the comments what you would like me to post about, and like the video. And I will see you in another video.